Okay, moving through limits. Now we're going to talk about definition, or now we're really going to talk about how to determine if a limit doesn't exist due to increasing or decreasing and without bound. Is it actually increasing or is it decreasing without actually looking at the graph? So definition of a vertical asymptote says that if f of x approaches either infinity or negative infinity from either the left or the right, then we know that there's a vertical asymptote there. Remember, it never actually touches the vertical asymptote. It just keeps increasing or decreasing. So here's one of our theorems in our calc book on vertical asymptotes. If you have two continuous functions on an interval containing the letter or the number c, as long as f of c does not equal 0, so this is telling me that if I use direct substitution, the top is not going to be 0. And the bottom does equal 0, so it is not in determinate form because top is a number, bottom is 0. What that means is there's a vertical asymptote there. So really what's that saying is if you have a non-removable point of discontinuity, you will have a vertical asymptote at that point. So like I said, what we want to do is determine if we're approaching either negative infinity or if we're approaching positive infinity. Typically in these types of problems, we do look at either the left-handed limit or the right-handed limit because oftentimes we are approaching positive infinity on one side and negative infinity on the other. One thing to be aware of is that this limit still does not exist. The equal sign does not mean the limit exists. It's just to clarify why the limit doesn't exist. So let's look at some examples. Suppose I want to determine each of the following limits. So I look at the first one, x is approaching 1 from the left, and I have the function x squared minus 3x over x minus 1. So the first thing I do is I try to factor this because I'm hoping I can use direct substitution. Well, I notice that after I factor this, nothing cancels. There is no way to rewrite this to use direct substitution. In fact, it looks to me that x equals 1 is going to be a non-removable point of discontinuity and therefore an asymptote. So I've already concluded that I have an asymptote there. So now I have to figure out what's happening at my asymptote. Am I approaching infinity or negative infinity? So since I'm looking at the left side of 1, I'm going to go ahead and pick an x value. So basically I'm making a table like we looked at before, but I'm not going to make as big of a table because I don't need to figure out what's going on. I just need to figure out if it's positive or negative. So I'm going to pick a value that's close to 1 but on the left side of it. So how about 0.99? And then all I'm going to do is I'm going to plug it in. So I'm going to plug 0.99 into my function. So I'm going to do 0.99 squared minus 3 times 0.99. I already know on the bottom 0.99 minus 1 is going to be a negative. So I go ahead and calculate the top, and I realize I get a negative on top as well. So I get negative over negative, which I know is positive. Therefore, this is going to approach positive infinity. If I look at the right side of this function, so now I pick an x value that is greater than 1, but not by a lot. So let's say I pick an x value of 1.001. What happens when I plug that in? Well, what about if instead of plugging it into the function in its form like this, what if I plugged it into its factored form? I may not need to do any calculating on my calculator because if I plug in 1.01 for this x here, I see I'm positive. And 1.01 minus 3 I see there is negative, so I have a positive times a negative on top. 1.001 minus 1 is going to be positive on the bottom. So that's going to give me a positive times a negative is a negative on top over a positive, which is going to tell me it's going to approach negative infinity. Looking at one more example like this, because it made it really easy for me on example 2 when I was able to plug into, the factored form, I'm going to go ahead and factor example 3 first. And plus maybe I'll get lucky and I'll be able to use direct substitution. So I approach negative 2 from the left, and I am going to do x plus 4 times x minus 2 all over x plus 2 times x minus 2. So I see I do have some removable point of discontinuity. I still can't plug negative 2, and it still makes my denominator 0 here. Actually, let me take that back. I plug negative 2 in, and I realize it makes my denominator 0 even after simplifying. And I noticed that I would get a number on top and 0 on bottom, so I'm not in indeterminate form, which makes me know that I have a vertical asymptote there. So I need to figure out, is my vertical asymptote approaching a positive infinity or a negative infinity? So I'm going to take a value on the left side of negative 2. So how about negative 2.001. Negative 2.001 is smaller than negative 2, getting closer towards negative 3. I'm going to plug it in on top, and when I plug negative 2.001 into x plus 4, I get a positive on top. When I plug it in on the bottom, negative 2.001 plus 2 is going to give me a negative on bottom. Positive over negative is negative, so this approaches negative infinity. Drawing your attention to something else, on page 84 in your book, I'm going to have you look at, it's called Theorem 1.15. Basically what it tells us is that if we multiply a number, well, let me start at the beginning of it. If we add or subtract a number to or from infinity, we are still going to be infinity. If we multiply a number by infinity, we're still going to be infinity. Unless that number is negative, then we'll be negative infinity. If we divide a number by infinity, we're 0. So let's go ahead and look at these two last examples. So I see I have negative 2 over cosine of x. So I'm going to say that's the same thing as negative 2 times the limit as x approaches pi over 2 from the right. And I'm going to say 1 over cosine of x is secant of x. And then, so instead of plugging numbers into secant of x, because I can't do that as fast in my head, I can graph secant of x in my head really fast. So I remember that in order to graph secant of x, I want to graph cosine. So I know at 0, cosine is 1. At pi over 2, cosine is 0. At pi, cosine is negative 1. At 3 pi over 2, it's 0. And it's 2 pi. So here is 1 period of my cosine graph. So secant, remember, is going to have those asymptotes every time cosine is 0. So if you remember this was pi over 2, I probably should have labeled that. So I notice that as secant, or when I approach an x value of pi over 2, as I get closer and closer to pi over 2 following my secant curve, I notice that I'm approaching negative infinity. So what is this telling me? It's telling me I have negative 2 times negative infinity, which I know becomes positive infinity. If I look at example, I think it's the 5th example, kind of the same concept here. So I'm approaching 0 from the left. So I see that I have the limit as x approaches 0 from the left of x plus 2. So I know cotangent is cosine over sine. So instead of dividing by cosine over sine, I'm going to multiply by sine over cosine. Well, now because I have a product, I can separate these, and I get the limit as x approaches 2. X approaches 0 from the left of x plus 2 times the limit as x approaches 0 from the left of sine x over cosine x. So I see here I can do direct substitution, so I get 2 times, and then actually I notice here I can do direct substitution as well, so I guess I didn't put a very good problem in here. So I get sine of 0 is 0, cosine of 0 is 1, so I get 2 times 0 over 1, which becomes just 0. So I guess I wasn't using one of my limit properties there. I apologize. I didn't, like I said, come up with a very good example for that. But still kind of that idea that I can break limits apart, multiplication, division, addition, subtraction. I can pull constants out or coefficients out to the front, and then I can perform my multiplication. And that is limits at infinity.